When we talk about the idea of processing sound, first and foremost, sound must travel through a medium. The easiest medium that we have on the planet for sound is air. Air is the closest thing we have to the absence of a medium. Because sound is a mechanical wave, it needs a medium to pass through. Okay? Now, what ends up happening is you are constantly receiving different types of sound waves. Right now, my voice has a certain pitch, so a tone to it, and it also has a certain volume. Okay? The amplitude of that wave is what decides on the volume. If I'm speaking really low, the amplitude of the wavelength is a lot shorter. And if I'm speaking at a louder volume, the amplitude of that wave is larger. So as sound waves come through the ear, they get trapped in what's called the outer ear. And the outer ear, okay, is made up of the parts that you can see. So the parts that are visible to the outside world, okay, these are the parts that your fingers can reach, put it that way. All right, your pinky can probably fit into to a certain extent, part of your auditory canal or your ear canal. But sound travels right now towards you, and the way that the outer part or the pinnae of your ear is shaped, it's actually shaped as a funnel. And you'll notice that sometimes when people when they can't hear you, they may cup their ears like this. And that's actually, it helps direct sound into the actual pinnae. And from the pinnae, sound gets diverted into the auditory canal. These two parts, we still can't actually see the sound wave. All right? It's still traveling, it's still disrupting the air. From the moment it enters what we call the middle ear is where we actually see or we can visualize that mechanical wave. Because that wave through the air gets translated by the first part of the middle ear, and it transforms it. It goes from auditory energy going through the air, and it transforms it to kinetic energy, actual movement of different parts. Okay? And from that moment on, from the moment it gets into the middle ear and beyond into the inner ear, that wave is actually visible. Okay? It's reflected in the motion of the different parts. If something has a higher pitch, okay, a really high voice, it will vibrate very quickly. If something has a lower pitch, it will vibrate more slowly. Okay? And we know that volume has nothing to do with the rate at which things vibrate. It has everything to do with the size of the actual wave. So, outer ear. The pinnae acts as a funnel to make the sound go from the wide open outside into, and it focuses it into a smaller opening. All right? That canal that we actually clean with Q-tips and what have you, if you've ever used a Q-tip, has it ever happened to you that you may have pushed the Q-tip too deep into your ear and it really, really hurts? Okay? If that's the case, that means you've gotten to the end of the actual auditory canal and you're basically pressing on something that's part of your middle ear. In the actual outer ear, we can't see any of the mechanical waves. Okay? We know they're there. We can measure them in the air, but we don't actually see physical proof of them. But that changes when we go from the outer ear to the middle ear. Okay, the middle ear starts off with your eardrum. all right, also known as your tympanic membrane. In French, we call it le tympan, all right? And if you've ever played a tambourine or a little hand drum like that, the idea of a drum works exactly the same way as and produces exactly the same kind of sound or vibration that the eardrum is producing. As these sound waves travel through the air, and we will draw a sound wave here in, let's say, I don't know, pink. We'll draw our sound waves coming in. As they come into the ear, they hit the tympanic membrane or the eardrum, and depending on the frequency of the wave, they will cause it to vibrate. And this is where that chain reaction of events starts. As soon as one thing starts to vibrate, the next thing that's touching it will then vibrate as a result. And so on and so forth until we get to the end of the line. When we talk about the middle ear has 4 specific parts to it. These, and 3 of them, are the smallest bones in the human body. All right? Your book refers to them as the ossicles. I want you to know their names and know which one comes in what order. All right? We start off with our eardrum, which is basically a very thin, flat surface that basically covers, it's like a piece of saran wrap over the auditory canal. It's a very thin piece of tissue. And it is perfectly sealed around the auditory canal. Okay? It is what divides the inside of the ear with the outside world. It is what will start to physically vibrate. So your eardrum then has the first of the ossicles sitting on it. It is called the hammer. The hammer will start to vibrate at whatever frequency the eardrum vibrates at, because they're touching, and it will cause the next bone, which also touches the hammer, to start to vibrate. That second bone is called the anvil, simply because it looks like an anvil. An anvil is just kind of something with a small base and a wider top. You see a lot of that with blacksmiths. You'll often see thunderclouds take the shape of an anvil. And then finally, you have the smallest bone in the body that's touching the anvil, and it's called the stirrup. It's called that because it looks just like a stirrup on the side of a horse's saddle. Okay? It's got the top of the stirrup here, and these 2 little ends here actually touch the ending of what's known as the middle ear. So we know that our sound wave goes from invisible to visible once it gets to the middle ear. It starts off causing the eardrum to vibrate at a specific frequency. Because the hammer's touching the eardrum, it vibrates at the same frequency. The anvil touches the hammer, it vibrates at the same frequency. Same can be said for the stirrup. Now the stirrup is touching this hollowed out chamber of bone called the vestibule. Okay, a vestibule is a word given to any kind of little opening area. Okay? Inside the vestibule, we have liquid. The ear is filled with, the inner ear is filled with liquid. Okay, very similar to water. And what ends up happening here is the sides of the stirrups are hitting that bone, and they're causing the outer shell of that vestibule to vibrate, which causes the liquid inside the vestibule to move around and vibrate. This actual vibration gets carried along to the next part of the inner ear called the cochlea. The cochlea looks like a snail's shell. And inside that cochlea, we have our sensory receptors. These little hairs that stick out of the cochlea, and as soon as the liquid in the vestibule and the cochlea starts to vibrate, those little hairs start to move at whatever rate, okay? They start to wave. And depending on the frequency of the wave and the amplitude of the actual wave that they're creating, they create an auditory impulse. And that message gets sent via the auditory nerve to the actual brain. So our vestibule starts to vibrate because the stirrup is hitting it. The liquid inside the vestibule, all right, is going to vibrate at the same rate that the bone surrounding it vibrates. That liquid goes all the way from the vestibule into the cochlea. And inside the cochlea, we have our little sensory receptors, our little hairs, okay, all throughout the actual cochlea. And each one of those hairs is linked to the beginnings of the auditory nerve. You have two auditory nerves, one for your right ear and one for your left ear, okay? What ends up happening is those little hairs are immersed in liquid. And whatever the frequency is and the amplitude of that wave, those hairs will sit there and vibrate. Okay? Those hairs are your auditory sensory receptors. They're just like the rods and the cones in the eye, except they use mechanical waves. And that sends a bunch of impulses to the actual auditory nerve, to the auditory processing center of the brain. These little tubes up here, okay, are known as your semicircular canals, and that is basically the levels of your body. It's what helps your body maintain its balance. Okay, so there's a lot that happens here. You need to be able to outline the path that a sound wave makes from the moment it enters the outer ear until the moment a nerve impulse is sent to the brain. All right? Now, I just want to talk briefly about sensory reception. Okay, if this is a person's eye here, talk about the nose, there's a face, okay, and then this is a person's ear, right here with the opening. Okay, the auditory canal is right here, let's say. All right, if we look at that and we see, put that right here, we see that a person's brain is also inside their head, like so. There's your cerebellum, and here's your brainstem, down your spine. If we look at processing time, okay, distance-wise, your ear, so this portion right here gets processed right here in the brain. Your eye, right here, actually gets processed back here in the brain. So when we talk about reaction times, it's a shorter distance for a sound wave to actually go from the outer ear to the point at which in the brain that it's analyzed and determined what it is, than it is for a light stimulus to go from the eye to the actual, visual processing portion of the brain. So in theory, ears are better and quicker at responding to stimuli than eyes are. It's one of the reasons that they actually always associate not only a flash, but a sound for start pistols, whether you're swimming or racing or whatever. Okay, the flash is there because yes, we're talking a few hundredths of a second. The flash is there for any auditory impaired people, but the sound is what actually travels faster.